Now let's look at the multivariate case. As we previously see, each observation has multiple aspects, and those aspects could be captured by those variables. For instance, the years of education that you have received, the race background, the age group that you're in, the income, and stuff like that, right? So the previous model, which was univariate, was then excessively naive. And here, we're going to utilize multivariate case to capture many more aspects and to analyze their influence on the dependent variable, in this case, cigarette consumption. Okay, so here we should change our interpretation of coefficients slightly. So let's look at the model. Here we have multiple variables. Okay, so we have y equals to beta 0 plus beta 1 x 1 plus beta 2 x2 plus beta 3 x3 plus u. This is the population. And then we use a model to estimate, we use a model based on the data to estimate for this population. So we have the fitted line or the regression. Which is this. Okay, so this is the fitted line, namely the regression. Okay, so here, what does each coefficient mean? I mean the slope term. Okay, I just the interception term, we know what this means. We just leave it here. The more important is the slope term. Okay, so for instance, beta 1. What does that mean? Beta 1 is actually the derivative, the partial derivative of y with respect to x1, of y hat with respect to x1, right? If you take the partial derivative with respect to x1, in your eyes, only x1 is the variable. Everything else are just constant added to it. And when you take the derivative, they're all ignored, right? And beta 1 hat is then the result of the derivative. And what does this mean? This means you're actually holding everything else constant, which is exactly what this partial derivative means, right? When you're taking partial derivative with respect to x1, x1 is the only variable in your eyes. That means you're holding everything else, including x2, including x3, constant. Or here we say specifically x2 and x3 are emphasized as being held constant. Okay, therefore beta 1, then beta 1 hat is the ceteris paribus, meaning holding everything else impact of x1 on y. So this is how you should interpret the coefficient. And similarly, beta 1 without hat, which is the population coefficient, then that represents the ceteris paribus influence of x1 in general, right, in the population on y. Okay, so this is the interpretation change. And now let's look at let's look at the problem. So we were still working on this smoking example. Okay, so now let's say we are expand our model to also investigate how age and income affect cigarette consumption, which are here, age and income. Coloring sometimes makes things easier, right? The impact of age and income on cigarette consumption on top of education. Okay, so that means you should also include education in the regression. So what I'm gonna do, let's first write out the population of this example. Example on page 16. And let's write out the example. So here, in the context, it should be cigarette consumption. So the population relationship should be cigarette consumption equals to beta 0 plus beta 1 x1, which is still education, plus beta 2 age plus beta 3 what is that? Beta 3 income. Okay. Don't forget to add the turbulence term, the error term, U. All right, so this is the population. And then the regression should then be cigarette estimated equal to beta 0 estimated by the model, by Excel, beta 1 by education, plus beta 2 hat by age, plus beta 3 hat by income. And here we just need to work it out through Excel to then we can replace beta 0 hat, beta 1 hat, and beta 2 hat, and beta 3 hat according to the number reported by Excel regression. Okay, so what we're going to do is then we're going to tend to Excel. Okay, and we're going to utilize data analysis function regression. So now we're going to input the Y is still F, which is cigarette consumption, that's right. But X, we need to input more. We have the A column, and then we need to input D and E column. And to include all the variables. So see, it can only you can only include columns that are next to each other. So what we are supposed to do here is, let's just forget about this for a while. We need to first move all the columns that you are to work on, okay, to be adjacent with each other, to be next to each other. Okay, then let's use data analysis regression. So your Y is still F column, that's right. But your X now is all the 3 columns together. So let's go to 808. And we need to specify, tell Excel that the first column is label. And we are to go with new worksheet, which is regression multiple. Meaning multiple variables, independent variables are included. Report. Okay, regression multiple. That's exactly here. All right. So what do we have? What do we have here? We have the regression. Okay, and we have education, age, and income, and those are the coefficient of them. So here, the intercept is again beta 0 hat. Education is beta 1 hat. and age is beta 2 hat, and income is beta 3 hat. Okay, then as you're reporting this in the context, you just need to replace those numbers. So you have cigarette consumption equals to 12.85. That's your slope term. That's your intercept term, plus beta 1, which is the coefficient of education, and here that is minus 0.378 by education, plus, I'm sorry, that's another minus 0.042 by age, plus 0.0001 by income. Okay, and don't forget to report the standard error, 2.576, and here 0.16770, and here 0.0287, and here if you are not familiar with this E thing, what I would suggest is to select everything, change the format of cells into number, keep 4 decimal. So here we have 0.0001 as the result. Okay, and then we are going to test the statistical statistical influence of age and income on cigarette consumption. Okay, so first, before that, we need to interpret the coefficient of age. So that's question 3. So let's look at this. So question 3, okay. So question 3, the coefficient of age, that is minus 0.042. So what does this mean? That means your age increase by 1 unit, which is 1 year. Cigarette consumption will decrease is estimated to decrease by 0.042 again units. Could be packs, could be 10 packs. It's based on the units that your data is at. Okay, so that's the coefficient of age. How do we interpret it? And here you can see holding everything else constant. Okay, so that's number 3. Number 4, test the statistical influence of age and income on cigarette consumption. Age and income. So how do we do that? Let's use age as an example. So T-stat, in this case, first you are testing the statistical influence of age on cigarette consumption, right? So first, let's construct the hypothesis. H0 is that age has no impact on consumption, and you're always hypothesizing on the population. Okay, so you're guessing beta 2 equal to 0. That's what you guess. Okay, and the alternative is beta 2 is not equal to 0. So now let's see. Method 1, T-stat. In this case, T-stat of age, of the coefficient of age, is minus 1.45. Okay, its absolute value is 1.45, which is smaller than 1.96. So that is considered not to be too far away, not to be in the rejection zone, which should be different from this estimated value, right, by a t-stat higher than 1.96, and here it's not the case, then shouldn't reject H non. Okay, if we don't reject the H non, then we consider beta 2 to be no much different, not significant different from 0. That means age doesn't impact cigarette consumption significantly. Okay, so that's your first one. Second one, p-value. Your p-value should be smaller than 0.05. For this case, it's a 95% confidence level, right? But here, the p-value is 0.147 or 0.148, which is greater than 0.05. Again, we have the same conclusion. We can't reject H non. There is no statistical significance. Namely, age doesn't impact cigarette consumption significantly. The third one, confidence interval method. In this case, the 95% confidence interval is from minus 0.0982 to positive 0.0148, and this range contains 0. Again, the conclusion is beta 2 therefore isn't significantly different from 0, because in your 95% confidence, 95% of chance, it's 0 is in there. Okay, and we have the same conclusion that age doesn't impact cigarette consumption significantly. Okay. And here for income, let me just quickly verbally illustrate income in this case. Okay. So for income in this case, the t-stat is higher than 1.96. The p-value is smaller than 0.05. And the confidence interval supposedly doesn't include 0. It's very close to 0, but still not include. Okay, because here, look at t-stat, look at p-value, they are not too much different from the respective threshold. T-stat is only a little bit higher than 1.96, and the p-value is a little bit lower than 0.05. That's why the confidence interval doesn't really seem to be too much different from 0, but you can rely on the previous two methods to tell you that income actually has a significant impact on cigarette consumption, according to this model. So if I were to add the last thing, another thing, I would say, what is the overall goodness of this model? The overall goodness of this model is reported by R squared. And here you can see it's 0.01. That means there is 1% of variance explained by this model as a proportion of entire variance in the model, in the data. So if we were to compare this to the previous one, which is here, okay, that was less than 1%. So here, by by including more variables, we actually improve the goodness of fit for our model. The model actually fits better. So this is the multivariate case of regression.